All right, so this is the first of two parts finishing this unit on trigonometry, in which we kind of redefine our understanding of trigonometric ratios away from right triangles or triangles in general and towards rotations, which is what we're kind of introducing in the last lesson. And so if you want to think about trigonometry and we want to think about the sine, cosine, and tangent ratios or functions in terms of rotations, we need to redefine them slightly. And so again, what I have here is an angle in standard position. The arm in red is the initial arm, the arm in blue is the terminal arm, and this point in black is just the coordinates, x comma y, of some point on that terminal arm. And if there's some point on that terminal arm, there's a distance, and the distance from here to here we call r, and that r is for the radius, because if you imagine this terminal arm spinning around, this point would trace out a perfect circle of radius r. And again, we want to think about rotations. We want to think about angles in terms of rotations. And again, when we think about rotations, it can be any number, positive or negative. And so if I look at this, I can start to see how this can connect back to sine, cosine, and tangent if I imagine there being a right triangle here, because your x coordinate is kind of related to your distance along the bottom of this triangle. And your y coordinate is related to the height of this triangle I drew. And your radius is related to the hypotenuse. So for example, if we thought of this as a triangle, a right triangle with angle theta right there, we would say the sine of theta is opposite over hypotenuse. In this case, the height, which is y, over the hypotenuse, which is the radius. And so what I have here is a different way of defining the sine ratio in terms of a point on the terminal arm and the distance of that point from to the origin. And again, it's more abstract than what you learned in grade 10, hence we don't learn about this generally in grade 10. But I can now redefine sine as y over r. But again, y is a coordinate of some point on the terminal arm, r is the distance of that point to the origin. Cosine, if I did something similar, would be the adjacent side of the angle over the hypotenuse, or in this case, the x divided by r. And tangent would be y over x. And so what I have here are just different, but very related to what we learned before, but different definitions of sine, cosine, and tangent. And again, the key is realizing that x and y are coordinates, which means they can be negative, and r is a distance, so it's always positive. And as well, if I think back to this right triangle here, the kind of beginnings of trigonometry is the Pythagorean theorem, in which we'd say a squared plus b squared equals the hypotenuse squared. In this case, we could think of it as x squared plus y squared equals r squared. Again, essentially just the Pythagorean theorem right there. All right, and so that equation there, which is just the Pythagorean theorem with x, y, and r instead of a, b, and c, is what relates these three variables together, x, y, and r. All right, so let's look at this. Let's show an angle in standard position that goes through -3 comma -4. So first, let's visualize that. -3 comma -4, that's a point. 3 to the left, 4 down, so I can visualize that quite nicely. -3 comma -4. And I'm saying the terminal arm of an angle in standard position goes through that point, which means if it's an angle in standard position, it always starts right here. And the terminal arm must therefore look something like this. Here's my terminal arm. Now with that said, how did the angle get there? Probably you're visualizing something like this. But I will say that's not the only way the angle could have got there, right? It could have gone there this way, or it could have gone around more than once, and so on. But I'll keep it like this, and I'll just call that theta. I'll call that angle theta. Although again, just because we know where it ended off doesn't mean we know exactly how it got there. That's it. Even though I don't know exactly what theta is, I don't know exactly how the angle got from the beginning to the end, I can still find the sine of theta, because the sine of theta we saw is the same as y over r, or in this case, -4 over r. But what's r? Well, r is the distance from here to here. How do we find that distance? We could create a triangle and use the Pythagorean theorem, or we can just jump straight to that x squared plus y squared equals r squared that I mentioned a moment ago. Because we know x and we know y. X is -3, y is -4, which means I'll know r in just a second. Remember, a negative times itself is always a positive, so I have 9 plus 16 equals r squared, which means 25 equals r squared, which means r equals 5 units. That's a convenient number. So I know that distance I've highlighted in green is exactly 5. And so now that means the sine of this angle is negative 4 over 5. And the cosine of this angle, cosine is x over r, so in this case, negative 3 over 5. And the tangent of an angle in center position is y over x, so in this case, negative 4 over negative 3, which I might as well simplify this down to just 4/3. So that's it. What's that angle? What is that angle in green? Well, how can I figure that out? Well, I can use really any of these equations I just wrote down for sine, cosine, or tangent. The simplest is probably tangent, because tangent of theta equals 4/3, which is a positive number. The other two are equaling negative numbers, which we'll talk about shortly enough, but I don't need to think about them. It's a little bit weird right now that they're equaling negative numbers. At least that may seem kind of weird to you. That said, I know that the tangent of theta equals 4/3. So how can I figure out that angle? Well, I can use the inverse of tan. And so I can go the inverse of tan of 4/3. And I go to my calculator, type in the inverse of tan, and it tells me an angle that's pretty close to 53 degrees. Now, 53 degrees, let's pause and think about that for a moment. There is no way theta is 53 degrees. There's no way that angle in green is only 53 degrees. I can see it's more than 180. So what does that 53 degrees represent? That's not my overall answer, because remember, there's many ways an angle can end up in this position. 53 degrees is the reference angle, which we were introduced to in the last lesson, which means 53 degrees is this angle from here to here, which means I know this angle in green is 180 plus 53 degrees. So that angle I've sketched out early on is about 233 degrees. I say about because I did round 53. And so keep in mind that by me using the calculator, the inverse tangent function to get that 53 degrees, that 53 degrees wasn't my answer, but it wasn't meaningless either. All right, so let's now talk about what we call quadrant angles. The trigonometric ratios at 0, 90, 180, 270. So let's look at a 0 degree angle. And again, all angles in center position start right here. So what's the sine of 0? What's the cosine of 0? What's the tangent of 0? Well, you could use a calculator right now, although it's kind of silly. But if you use a calculator, you get 0, the sine of 0 is 0, the cosine of 0 is 1, the tangent of 0 is 0. OK. But I don't need a calculator to get that. So let's remember, for example, the sine of any angle is an x-coordinate divided by r. And sine is y over r, cos is x over r, and tan is y over x. So I can get these values for each of these without a calculator by just looking at this 0 degree angle, picking a point on it, and let's find that coordinate. The x-coordinate can be any positive number I want. Why not 1? The y-coordinate I know is 0. And so if x is 1 and y is 0, the radius is the distance from there to there. I don't need to use the Pythagorean theorem to know that if this is a perfectly horizontal line, that is also 1. So now I know the radius is 1. I know my x is 1. I know my y is 0. And notice what I get. If I go into these, the sine of 0 is going to be the same as 0 divided by 1, which is 0. Cosine of 0 is going to be the same as 1 divided by 1, which is 1. And the tangent of 0 is going to be the same as 0 divided by 1, which is 0. So like I said, I didn't really need a calculator at all for this. All I need to do was remember what sine, cosine, and tangent mean in terms of an angle in center position. And remember, a 0 degree angle, I should have a little degree symbol here, doesn't make any sense in a right triangle. You can't have a right triangle with a 0 degree angle somewhere. It's not possible. So the sine of 0 doesn't really make any sense in terms of a triangle, but it does make sense if we reinterpret how to define sine, cosine, and tangent. So let's look at 90 degrees. And so for this one, if I want to find the sine of 90 degrees, if I want to find the cosine of 90 degrees, or if I want to find the tangent of 90 degrees, I can just pick a point on here. I know the x-coordinate is 0. The y-coordinate can be any positive number I want. Why not 1? Which means, again, the radius is exactly 1. And so sine is y over r. So in this case, it's 1 divided by 1. So I know the sine of 90 is 1 without using a calculator. The cosine of 90 is x over r. So it's 0 divided by 1. So I know it's 0. And the tangent of 90 is y divided by x, or 1 divided by 0. And 1 divided by 0 is undefined. Division by 0 doesn't make sense. So the tangent of 90 is undefined. And if you type the tangent of 90 to your calculator, it's going to give you an error or some sort, or it's going to say it's undefined. And so I can do the similar thing for 180 and 270, just to not make this take forever. I'll just get straight to the answers. But again, I could pick a point. I would pick the point -1, 0, because they're just nice clean numbers. If you use that, or if you use your calculator, the sine of 180 degrees, you'll get 0 again. The cosine of 180 degrees will be exactly -1. The tangent of 180 degrees will be exactly 0. And if you look at an angle going straight down like this, 270 degrees. And if you pick a point on there, again, I would pick 0, -1. Or you could use a calculator. The sine of 270 degrees is going to equal -1. The cosine of 270 degrees is going to equal 0. And the tangent of 270 degrees is, again, going to be undefined. If you use this particular point, you get -1 divided by 0. All right, and so these are, again, what we call quadrant angles. Very important angles, multiples of 90. Okay, well, you may have now noticed that at times we look at certain angles and the sine function is positive. Sometimes the sine function is negative, like I can see right here. Sine function is positive, sine function is negative. And same thing for all my functions. Sometimes cosine is positive, sometimes cosine is negative. Same thing for tangent. Well, where they are positive or negative is based on which quadrant they're in, because the quadrants determine if the x or y values are negative or positive. And so in general, in quadrant 1, an angle is something like this. Any angle in quadrant 1, your x, y coordinates will always be positive. So it doesn't matter if you're looking at the sine function or the cosine function or the tangent function. They're all going to equal positive numbers in this quadrant. So all trigonometric functions will, no matter what angle you put in, if it's in quadrant 1, so most likely between 0 and 90, you'll get a positive number out of each of those, always. What about quadrant 2? Quadrant 2 is somewhere in here. Well, in this case, your y coordinates are still positive, but your x coordinates are negative, and that'll affect some of these things. The sine function will still be positive, because sine is x over r. It has nothing to do with y. The cosine function will become negative, and the tangent function will become negative. So only sine is positive in that quadrant. Quadrant 3 looks an angle that ends up somewhere here. Similarly, it's going to change some things. In this case, x and y coordinates are both negative, and so that'll make your sine function negative. That'll make your cosine function negative. But your tangent function will be positive, because you have a negative divided by negative. And lastly, quadrant 4, any angle that ends up, let's say, there. Your x coordinates are positive, your y coordinates are negative, so sine will be negative. Cosine will be positive, and tangent will be negative. So you may have noticed that for each of these, I highlighted in blue the function or functions that were positive in that quadrant. And in quadrant 1, they're all positive. In quadrant 2, it's only sine. In quadrant 3, it's only tangent. And in quadrant 4, it's only cosine. And so I can actually memorize this really, really easily by just remembering 4 letters. A, S, T, C. And we quite often call this the cast rule. It's not really a theorem or anything. But you can look at the letters C-A-S-T. It spells the word cast. If you can remember these 4 letters in these 4 places, then you can remember that all the trigonometric functions are positive in the first quadrant. Only sine is positive in the second quadrant. Only tangent is positive in the third quadrant. And only cosine is positive in the fourth quadrant. And so, for example, if only cosine is positive in the fourth quadrant, that means I know sine and tangent are negative there. And so everything I have right here, which maybe looks like a lot, can all be summarized and memorized really quite easily just by remembering these 4 letters in this order. And quite often we say stuff like, all students take calculus, which is not true. But if you can, again, anyone can remember 4 letters in this order. But the order does matter. And then we know exactly in any quadrant where our functions are positive or negative. And with that said, let's kind of put some of these things together for a question like this that is quite abstract, but won't require a ton of calculations in the end. So what do I have here, though? I have no visual. The terminal arm of an angle in standard position goes to the point -2 and negative root 12. Without using a calculator, determine at least one possible angle for this. Okay, so what does this mean? Well, first let's start by making a visual. It's an angle in standard position, so I know it starts off here, and I know it ends off going through the point -2, negative root 12. So -2 over negative root 12, I don't know, somewhere around here. It's in the third quadrant, I know that much. And the terminal arm goes to that point. So I've now visualized the first part. And the question's saying, without using a calculator, determine at least one possible angle. I say at least because this is probably the most straightforward angle to visualize. But again, how do we know it's not going this way? And we don't. There's always more than one possibility. But I'll stick with this, and I'll call that angle theta. All right, so how can I figure out that angle? Even with a calculator, but I don't need one. Well, let's think about what we know here. If I look at these values here, that's my x-coordinate, that's my y-coordinate. Which means I know everything I need to focus on the tangent ratio, because the tangent ratio is just based on, is just y over x. So even though I don't know theta yet, I do know I can say the tangent of theta must equal negative root 12 over negative 2, y over x. Again, I don't know what the angle is, but I know the tangent of the angle must equal negative root 12 over negative 2. Okay, well, let's clean this up a bit. First of all, a negative divided by a negative. Let's write this as just root 12 over root 2. Sorry, over 2 whole. Okay, that's a bit nicer. But what can I do here? Well, let's think back to our work with radicals from earlier in this course. Root 12, I can break up into root 4 times root 3 over 2. And root 4 is 2 whole, so I can rewrite this as 2 root 3 over 2. And suddenly, we can see how this actually simplifies quite nicely, because I can now cancel out a factor of 2 from the numerator and the denominator. And so I'm left with just root 3. The tangent of theta equals root 3. So that already is now hopefully sounding a bit more familiar. But still, how can I figure this out without a calculator? I will say one thing that's not wrong but requires a calculator is to go to your calculator and type the inverse of tan of root 3. And it will tell you an angle. It's not a bad idea, but we don't need to do it, so I'm not going to do it. So how can we figure out what this theta is without a calculator? Well, we can think back to our special triangles. And root 3 did appear in one of our special triangles. If we remember the 30, 60, 90 special triangle. So any triangle that has a 30 and 60, any right triangle that has a 30 and 60 degree angle is similar to this, where if the shortest side is 1, the longest side is 2, and the side in between is root 3. And so, where does tangent equal root 3? Well, if I look at this triangle, if I look at the 60 degree angle, from 60 degrees, tangent is opposite over adjacent. So I now know, and again, this actually came up in an earlier lesson, but without a calculator, I know the tangent of 60 degrees equals root 3 over 1, or just root 3, which means the tangent of 60 is root 3, which means it looks like theta is 60 degrees. But we've seen this before today. No, it's not. There's no way that angle in green can be just 60 degrees. So there's something wrong here. Or I shouldn't say something wrong. I'm just not done. 60 degrees, the tangent of 60 is root 3. But there's no way that angle I drew in green is 60 degrees. But again, that number's not meaningless. This is not my final answer. This is my reference angle. This is the angle from here to here. This is 60 degrees. And again, we call that a reference angle. So now that I know that 60 degrees is that angle right there, now I can piece everything together quite nicely, because from here to here is 180 plus an extra 60. So now I know that angle of theta must be 240 degrees, or at least that's one possibility. And again, if I wasn't using the special triangle, I could have got the answer if I went to a calculator and I typed in the inverse tan of root 3. The calculator would tell me 60 degrees. But I then still have to realize that's actually just a reference angle. That's not the actual angle I had here. Now that's it. If you're kind of surprised that a calculator or something is giving you the answer you don't want, my question is, why would it give you the answer you want? I mean, like I've said, there's many ways an angle can end here, so we can't assume that a calculator knows what we want. A calculator doesn't know anything. So it'll give us one possibility, but chances are there's a good chance it won't be exactly the one we want. Another quick answer I could come up with, though, besides 240, if I look at this angle going from here to here, that must be negative 120 degrees. And so again, that is a second of many other possibilities. But I'll stick with just my 240. All right, so notice probably feels significantly different from the trigonometry you've done before. It definitely still connects. There are a few little triangles here, but mostly we're thinking about rotations, and it feels quite different. It's definitely more abstract. We're thinking about a rotation in some point on a terminal arm. That's way more abstract than a right triangle that you can see and draw. And so chances are this maybe will take a bit more time to kind of grasp hold of compared to other stuff, like the sine law or the cosine law, because it's just less familiar.